In physics and more broadly science, we're used to making approximations for the sake of simplicity. For example, we often approximate the Earth as a point of zero size when calculating orbital mechanics or gravitational effects. Of course, this is not realistic, but it is a good enough approximation for most purposes. On the other hand, when we study the space around the Earth, we often approximate it as a vacuum, because the density of objects in space is so low that they don't really affect each other at these distances. However, the situation is completely different when it comes to the Earth itself. To understand the space around the Earth, we first need to understand the Earth and what makes it tick. And to do that, we need to look at everything, starting from the core to the atmosphere and beyond. Welcome to my channel. Today we'll be looking into the structure of the Earth and how it affects near space. The Earth is a big place, both in terms of its total volume and the variety of environments it contains. It's divided into a solid inner core, a liquid outer core, a mantle, and a crust. The inner core is mostly iron with a radius of about 1,200 kilometers. The temperature there can reach 5,000 degrees Celsius, which is comparable to the surface of the sun. If you were ever to visit this part of the Earth, you wouldn't even be able to breathe because of the extreme heat. But it is one of the most important parts of the Earth, because it generates our magnetic field. More on that later. Above the inner core is the outer core, which is also made of iron. The temperature here can reach up to 6,000 degrees Celsius, so the iron is in a liquid state. The main difference between the inner and outer cores is that the pressure is much higher in the inner core, keeping it solid despite the high temperatures. The convection currents in the liquid outer core are responsible for the Earth's magnetic field. These currents interact with the Earth's rotation, and the magnetic field lines become twisted, creating a self-sustaining magnetic field. This magnetic field protects the Earth from the solar wind, which is a stream of charged particles coming from the sun. The next layer of the Earth is the mantle, which extends from the outer core all the way to the crust. The thickness of the mantle is about 2,900 kilometers, and it makes up the largest part of the Earth's volume. Unlike the core, the mantle is not made of iron. It's mostly made of silicate rocks. Also, unlike the core, the mantle is not a homogeneous medium. It has two different layers, the upper and lower mantle. The boundary between them is at about 700 kilometers depth. The main difference between these two layers is the temperature. The upper mantle is relatively cool, with temperatures ranging from 300 to 700 degrees Celsius, while the lower mantle reaches temperatures of up to 3,700 degrees Celsius. Despite the huge range of temperatures, the mantle behaves like a very viscous fluid on geological timescales. It can flow and deform, but it's too viscous to be easily moved around. The convection currents in the mantle drive plate tectonics, which is the movement of the Earth's crust. These currents arise because the Earth's core is hot and the heat flows outwards through the mantle. Finally, we reach the outermost layer of the Earth, the crust. The crust is the thinnest layer of the Earth, with a thickness ranging from a few kilometers to about 70 kilometers. It is also the coolest part of the Earth, with temperatures ranging from a few degrees Celsius at the surface to about 1,000 degrees Celsius at the boundary with the mantle. The crust is divided into two types: oceanic and continental. Oceanic crust is thinner and denser than continental crust, and it's found under the oceans. Continental crust is thicker and less dense, and it's found, well, on the continents. The Earth's crust is not static. It's constantly being recycled as old crust is destroyed and new crust is created. This process is called the rock cycle. The Earth's crust and the upper part of the mantle together form the lithosphere, which is about 100 kilometers thick. The lithosphere is divided into tectonic plates that move around on top of the mantle. The movement of these plates causes earthquakes and volcanic activity. Most of the Earth's volcanoes are located along the boundaries of these plates. Earthquakes occur when the plates suddenly slip past each other. The energy released during these slips can cause the ground to shake, which we experience as earthquakes. The Earth's atmosphere is the layer of gases surrounding the planet. It's divided into different layers based on temperature. The lowest layer is the troposphere, where most of the weather happens. The troposphere extends from the Earth's surface to about 8 kilometers above sea level. Above the troposphere is the stratosphere, which is the layer where the ozone layer is located. The ozone layer absorbs most of the sun's ultraviolet radiation, protecting life on Earth from its harmful effects. Above the stratosphere is the mesosphere, where most meteors burn up in the process called ablation. Finally, there's the thermosphere, where the air is very thin and the temperature can reach thousands of degrees Celsius. The thermosphere is where the International Space Station orbits. The Earth's atmosphere is held to the planet by gravity. Gravity is a force that pulls objects towards each other. The strength of gravity depends on the mass of the objects and the distance between them. The Earth's gravity keeps our feet on the ground and also holds the atmosphere around the planet. The Earth's gravity also affects objects in space around the planet. For example, it keeps satellites in orbit around the Earth. The Earth's gravity extends far out into space, but it gets weaker the farther away you get from the planet. Another important aspect of the Earth is its hydrosphere, which is the sum total of all the water on the planet. About 71% of the Earth's surface is covered by water, which is essential for life as we know it. The hydrosphere includes all the water on the Earth's surface, from the oceans to lakes and rivers, as well as the water vapor in the atmosphere. The ocean is the largest body of water on the Earth, and it plays a major role in regulating the climate. The Gulf Stream, for example, is a current in the Atlantic Ocean that brings warm water from the tropics to Europe, making the continent warmer than it would be otherwise. The ocean also plays a role in the rock cycle. As the ocean water interacts with the Earth's crust, it can cause rocks to weather and erode. This erosion can break down mountains and create new land. Finally, let's talk about the Earth's biosphere. The biosphere is the part of the Earth that is inhabited by living organisms. This includes the atmosphere, the crust, and the hydrosphere. All the living things on the Earth, from bacteria to plants to animals, are part of the biosphere. The biosphere is a complex web of interactions between living organisms and their environment. For example, plants use the sun's energy to make their own food through photosynthesis. This, in turn, provides food and oxygen for other living organisms. The biosphere also includes the remains of dead organisms, such as fossils, which can provide clues about the history of life on Earth. The biosphere is a dynamic and constantly changing system, and it is important to understand how it works. If we want to protect the delicate balance of life on Earth, when studying space, we often assume that the Earth is just a point of zero size. However, the Earth is a complex and dynamic planet with a rich history and diverse environment. Understanding the Earth is crucial for understanding the space around us. So next time you look up at the stars, remember that the Earth is just as fascinating as the cosmos above us. Thank you for watching, and see you in the next video.